Hello, this is section 3.5 in your book, which talks about determining which side of a reaction equilibrium, either the reactants or the products, is favored during an acid-base reaction. Now, this is something that we kind of touched on in 3.4 and we'll be touching on more in this chapter, as this is a pretty key part of the functional use of pKa's and the qualitative determination of relative acid strength that we're learning in chapter 3. Now, let's start looking at this reaction here, which is a general acid-base reaction that is reversible, meaning that both HA and HB are weak bases. So we know this reaction happens first because the lone pairs of B take the proton from A, releasing the electrons back to A to create A minus and HB. All right. So in this chapter, what we need to do is figure out first what the conjugate acid and conjugate bases are here, and then we need to determine which conjugate base is the most stable. Because if you remember, in our effort to make a qualitative model for easily determining acid strength, we are determining which conjugate base is the most stable because the most stable conjugate base gives you the strongest acid. All right, so in the reactants here, let's first find the acid and the base. That way we can determine what the conjugate acid and the conjugate base are. Hopefully this is fairly review. So the acid is here, and the base is here, right? Base is labeled B, A is labeled acid, but the conjugate acid of the base is here, and the conjugate base of the acid is here, right? Because coming the other way, the electrons on A can serve as a base, and we can get our original base back when the electrons between the hydrogen and base go back to the base molecule. All right, so now that we have the acid and base and conjugate base identified, now we can determine which, which basic molecule is actually the most stable. And by basic molecule, I mean we now have two sets of acid-base pairs, right? We have these two. Let's do it this way. We have these two here, and we have these two now. And in both cases, the bases are here, right? So that means we need to determine relative stability, which is more stable, B or CB in this case. Okay, so this has all been in very general terms. And in fact, there is no, we're not going to use boron and carbon boron, you know, B and CB. We're going to use actual weak acid and base molecules. So let's have a look at these two that we'll draw right here. So let's use something like no, I don't want to do that. Let's do this. There we are. And to this, we will add this is an okay version. There's a very similar question like this in your book. Right. So here we have some equilibrium. There we are. And oh, let's make this one red. There we go. Okay. So this pinkish one, it would serve here as the, oh wait, actually, this one should be NH, right? Yeah, there we go. Okay, now I'm on board. So then now we have this NH plus there we go. That's very sloppy. There we go. Much better. Okay, so these are our two molecules now. So let's find the acid and the base. So first, the conjugate or the acid is this one, right? Because we can see that in this reaction, lone pair must take one of those protons. Let's draw these out here. That way it's easier to see. There we are. Okay, great. And then the atoms from that proton must go back to the nitrogen. And its conjugate base must be this one here. It's also drawn in different colors, so it's easier to see. And the base must be this one, and its conjugate acid must be over here. Okay, so that means, again, we have these two and these two together. All right, so then which one is most stable? We are looking at this molecule, or we're looking at this molecule. And now it actually gets pretty simple because we're just going to use our ARIO rules. So in our ARIO rules, we can't use the atom, right? Because both negative charges are on the same atom. Can we use resonance? Both of them might not have the same resonance. So let's see. So in this first one, the resonance form could be like this. There we are, with the minus charges on the oxygen. And for the other, similar resonance form, the minus charge is on the sulfur. So the question for you all is, what is the most stable anion here? And hopefully you remember from the A part of ARIO, it's kind of like an inception problem because we're working on R right now, but we're generating a negative charge now in a resonance form on two different atoms. So we have to go back and check A again for each atom. And hopefully you remember that oxygens are more electronegative than sulfur. And so the oxygen is more stable. And so since the oxygen, the pink one, is more stable, that means that the acid A must be the strongest acid because its conjugate base is the most stable. I'll just write that in here. Whoops, I should say is the acid. Is the strongest acid. So reactants are favored. And there we have it. So now we can determine equilibria of reactions just based on using the ARIO rules that we learned. So this has been section 3.5.